I'll unplug my iPad. There we go. All right. Can everybody see my screen and see where it says mathing with sig figs? I did not write that, by the way. That's a Dr. Garcia thing. She likes to be silly anyhow. So here we go. So trying some problems and practicing our significant figures. And it says here, carry out the following arithmetic operations to the correct number of significant figures. I'm not going to do all of these. Well, let's just blast through a couple of them here. We'll start with A. Seems like a good place to start. Okay, so we'll start with A. Here we go. So 11,254.1 plus 0.1983 grams. Now, this is an addition problem, right? This is addition. And hopefully you remember the rules for addition were that the final answer can only have as many decimal places as the number with the fewest decimal places. And if you look at the first number, it has 1 decimal place, whereas the second number has 4 decimal places. And so we can only report the final answer to 1 decimal place. So when I punch this in my calculator, and I've already gone ahead and done this one, I get 11,254.2983 grams. So you get all that spinach, so to speak. Now, of course, we can only report this to 1 decimal place because of this number here, 11,254.1. And so we have the number 2, but it is followed by the number 9. And the rules are, if we have 0, 1, 2, 3, 4, the number remains the same. And if we have 5 or greater, which 9 is definitely greater than 5, we have to round this number up 1. And so what we end up with as a final answer is 11,002, oops, not 11 decimal. Dion needs to wake up. 11,254.3 grams would be our final answer. Let's give B a shot. You can see that this is a subtraction problem. I'll go a little bit faster here. So subtraction, the same rules apply. We have 1, 2 decimal places in this volume, and we have 3 decimal places in this volume. And so when you punch that into your calculator, you actually end up with 63.477 liters. But again, we can only have 2 decimal places. If I want to round this number, I look at the number that follows it. It's the number 7. 7 is greater than 5, equal to or greater than 5. So we're going to round this number up, and we're going to end up with, get my blue pen again, 63.48 liters. Let's try D. Let's move ahead and give D a shot. The next one is a multiplication problem. So this one's multiplication. This one here is a division problem, and you should remember that the rules for multiplication and division are very similar in that the final answer is going to be dictated by whichever number has the fewest number of significant figures. And so we have 0.0154. That number has 3 significant figures, and 88.3 also has 3 significant figures. So I'm going to take my calculator. I'm going to do this. You can't see me. I'm in my office here in my lonely basement, and I'm going to put here 0.0154, and I'm going to divide that by 88.3. And when you do that, you get 0.000174405. Now, I think there's a much simpler way to report that number, and that would be to use scientific notation. And so I'm going to convert that to scientific notation, and I end up with 1.74405, and it keeps going from there, multiplied by 10 to the -4 kilograms per milliliter. Now, again, I can only have 3 significant figures in this number. And I look at the number that comes after this 4, and it's a 4, and 4 is less than 5, and so we don't round that number off. And so when we report the final answer, we're going to get that it's equal to 1.74 times 10 to the -4. Let me don't leave out my units, kilograms per milliliter, like that. All right, let's move on from there and go to the next slide, which discusses the concepts and the definitions of accuracy versus precision. These are words that people like to use in their everyday speech, and oftentimes we don't use them properly Accuracy is how close a measurement is to the true value. So if you take a look at this target here that's on the far left, we have a dartboard here, and you can see some darts that are in that dartboard. And you can see that there's a bullseye, right? The bullseye is the dead center, right? And the thrower of the darts wants to hit the bullseye. And so you can see that all of the darts ended up very close to the bullseye. And we would call the bullseye the true value, right? That's where you want to get it. So we would say the shooter or the thrower of the darts was very accurate. Now, the definition of precision is a little bit different. It says how close a set of measurements are to each other. Now, focusing on that same target in A, you can see that not only are all of those darts very close to the bullseye, so they're all very accurate, you can see that they're all very close together, right? You can see they're all close. It says a close set, and this is a very close set that we see here. And so we say not only was the thrower accurate, but there is also good precision here. Now let's look at the next one. You can see that all of these darts are all clumped together. So right away we can say, hey, the thrower has great precision, right? Good precision. But is that accurate? Not at all, because the thrower was not even close to the bullseye. Now we take a look as the night wears on, you can see that the thrower maybe is in a pub or something and maybe has had a few too many pints, because in C here you can see that it's not accurate and it's not precise. The points where the darts hit the board are not close together, and they're nowhere near the dartboard, or sorry, nowhere near the bullseye. And so we would say that those points are not accurate, nor are they precise. And so stepping into the first exam and moving forward in this class, you should be aware of the definitions of accuracy and precision, because we use them quite a bit in this class. Now let's move on to a new subject, which is dimensional analysis, or the dimensional analysis method of solving problems. This is Mr. Dion's favorite way to solve problems, and I'm sure that many of you have been introduced to the concept of dimensional analysis maybe in high school or at another college or something, or maybe even in junior high, okay? I was introduced to it in high school, and the way that we use dimensional analysis is we determine which unit conversion factors are needed to get us the desired units that we wish to have in our problem, right? If we are solving some kind of problem and we want to get it the final answer in a certain unit, we got to figure out what that unit is first, right? And then we're going to carry units always through our calculation, and we're going to set up those units so that the units will cancel. All units are going to cancel except for the desired units, and that way we know that the problem was solved correctly. So if we have, for example, a given quantity and we multiply that by a conversion factor, we get our desired quantity. Another way of saying it is if we have a unit that we're starting out with in our problem, our given unit, we would multiply that by some kind of conversion factor that has the given unit in the denominator so that it can cancel out, and we end up with our desired unit, okay, our desired unit. Now, as a teacher, you're probably expecting me to say something like this, but I can't tell you how many times, okay, where is it here? How many times I've seen students botch a problem on an exam because they did not carry the units through their calculation. You know, I used to hand out paper exams when I taught this class face-to-face at PPCC. We'd all be in the room together, and I would give the students the exam. I'd give them some scratch paper, and I'd always collect the scratch paper at the end of the exam. It was a policy of PPCC. Still is, I assume, for paper exams. Anyhow, and sometimes I'd look at their scratch paper just like, hey, what did this person write down? And I'd seen many times where students missed an answer simply for leaving units out. And so units are very important. It really helps you know, okay, I'm on the right track. I probably have the right answer. So let's take a look at an example. Okay, mathing, I did not write that. That's the Dr. Garcia thing. But anyhow, let's take a look here. It says, a person's average daily intake of glucose, which is a form of sugar, is 0.0833 pounds. We use LB for the abbreviation for pounds. What is the mass in milligrams? And they give us this conversion factor here. Remember, I told you that if you need any conversion factor between metric and imperial or the English system, I will always give you that. Okay, so you don't have to memorize any of those. Now, I stuck this big giant picture of glucose tablets in the middle of this page. I don't know why, but anyhow, so it doesn't give me a lot of room, but let's take a look at this problem. Now, where do we start? We're given this number, 0.0833 pounds. And we want to end up with milligrams, right? Somewhere at the end, we want to end up with milligrams. And so we have to set up some kind of conversion factor to eliminate pounds, right? We want to cancel pounds out. Where did my pencil go? Here. Oops. Didn't mean to do that. Okay, so we want to cancel, we want to cancel pounds out. So how the heck are we going to do that? Well, looky, we're given a conversion factor right here, okay? So we could write that in 1 pound, there's 453.6 grams. Hey, looky, I've already eliminated pounds. And if I was to end my math right here, if I was just to put equals, I would end up with the final answer in grams, but I don't want it in grams. I want it in milligrams. Now, Bruce asked me, what kind of conversions do we have to have memorized? I'd say that you should memorize how many milligrams there are in a gram, but it's pretty, I don't like to use the word easy in chemistry class, but I think it's obvious that milli, 1,000, if you memorized the prefixes that I showed you last class, that milli is 10 to the negative 3. Another way that we could express that is we could say that in 1 gram, there are 1,000 milligrams. So a milligram is 1,000th of a gram. But I always like to use numbers that are bigger than 1. So I say 1 gram is equal to 1,000 milligrams. And we can use that conversion factor, right? The same way we used the other one that I have highlighted in yellow. And so let's try using that conversion factor. So we need to eliminate grams. So we can put that 1 gram is equal to 1,000 milligrams, like that. And looky, it's not magic. The grams are gone. And now we will end up with our final answer in milligrams. So let me just clean that up a little bit. And if you punch all of that into your calculator, which I didn't, so we have 0.0833 multiplied by 453.6. And we're going to multiply that by 1,000. And so when we do that, we get this big old number. Okay, we get 37,784.88. So it's a pretty big number. Now, my question for you is, and this might be a difficult question, but I'll just throw it out there. If you read the textbook, you'll probably have an idea how many significant figures should there be in this final answer. Yeah, so Julius says 3, Bruce says 3, Lola says 3, and you're all correct, okay? All of you are correct. So this is the number you get when you punch it in your calculator, this big old number here, right? Now, something that you can assume is that when you have a conversion factor, when you're given a conversion factor, you can assume that they have an infinite number of sig figs. So we have 3 significant figures in our weight, so 3 significant figures, and then we have infinity. What's a lower number, 3 or infinity? Well, 3 is a lower number. And so now I have to express this number, 37,784 and something, to 3 significant figures. Can anybody tell me what would be the easiest way to do that, to express it to 3 significant figures? What would be the easiest way to do that? Absolutely, Tyler. It would be scientific notation. And so if you click second function, SCI, on my calculator, which is a TI, I use a TI-30XA. It is a cheap calculator, okay? But it works, okay? And you press second function, psi, and it gives you the number in scientific notation. So, and when we round the 7, right, because 8 is greater than 5, or 5 or greater than 5, we round up, and so we end up with 37. We end up with 3.78 times 10 to the 1, 2, 3, 4 times 10 to the 4th milligrams, and that will be our final answer. All right, give me a thumbs up if you follow me on that one. All right, wonderful, good. All right, pretty reasonable problem, right? All right, well, let's keep on trucking here. Let's try another one. It says here, oh, there's a bunch of examples here at the end. It says, what? Did I do this one? Oh, I did. It says, an average adult has 5.2 liters of blood. What's the volume of blood in meters cubed? All right. Well, what kind of conversion factor are we going to use here? Well, let's see if we can dig some up out of our brains, okay? Because there's nothing given to us here, right, Bruce? So we're starting off with 5.2 liters. I'd say one of the first things we could do is convert the liters into centimeters cubed. And I'm going to throw this out there. Does anybody remember? I went over this last class. I had a slide that I showed you a big picture of a cube, and it told us how many centimeters cubed there was in 1 liter. Does anybody remember that? How many cubic centimeters or how many milliliters in 1 liter? Because a centimeter cubed and a centimeter cubed and a milliliter are the same volume. Exactly. There's 1,000, right? Yeah. Thanks, Julius. Thanks, Tyler. There's 1,000. Thank you, Deanna. There's 1,000 centimeters cubed in a liter. Now, I don't know how many meters cubed are in a liter or how many liters there are in a meter cubed. I mean, I can figure it out, but I don't have that off the top of my head. But I do know how many centimeters or centimeters cubed there are in a liter. And I tell you what else I know, and I'll just spit this out to you, is that I know that in 1 meter, there's 100 centimeters, right? There's 100 centimeters in 1 meter, right? Centi. Okay? And so we can use these two conversion factors. Let's try the first one. We want to get rid of liters, right? We want to cancel liters out. And so we would have to set it up with this conversion factor with liters on the denominator. So 1 liter is equal to 1,000 centimeters cubed. That gives us liters canceling out. If we stopped right here, we would have the volume of blood in what? In centimeters cubed. Okay, but we don't want that. We want it in meters cubed. Now let me show you a little trick. If you're asleep or if you're watching, Netflix and just have me in the background being like, I'm attending lecture, and I know that none of you would do that. Okay, but in case you are, I need you to wake up because this is something the students mess up all the time. I've seen it 100 times. Now watch, how would I do this conversion? Okay, if I know there's 1 meter, in 1 meter there's 100 centimeters. So I'm going to put 100 centimeters down here, and I'm going to put 1 meter up here. Now, I need to cancel centimeters cubed. Can anybody tell me, and I know it might not be easy by the chat, but can anybody tell me what I should do here with this conversion factor? Thanks, Julius. I like your answer. You cube it. Good. You express it to the power of 3, right? He's saying you take the whole damn thing. He didn't say that, but I did. You take the whole darn thing and you cube the entire thing, right? So if you take, and I'm just going to do it down here to show you, if you take 1 meter over 100 centimeters, right, and you cube the whole thing, you get 1 times 1 times 1, which is 1, meters times meters times meters, which is 1 meter cubed. And then if you take 100 and then you cube it, so to the power of 3, you end up with 1 times 10 to the 6 centimeters cubed. Okay, and I can't tell you how many times I've seen students botch that. Okay, they'll mess that one up. All right, and so you could take this and you could plug it in there if you want. I just like to leave the whole thing the way it is. I think it looks more elegant, makes you look maybe smarter than I really am. So anyhow, when you do all of that math together, okay, you end up with the final answer, which should only have 2 significant figures because we have 2 sig figs here. And remember, in our conversion factors, we assume that they have an infinite number of significant figures. And so when we plug all that spinach into our calculator, we end up with 0.0052 meters cubed. Or you could express that in scientific notation. We could move the decimal to the right, 1, 2, 3, like this. So you could express it as 5.2 times 10 to the negative 3 meters cubed. Either one is perfectly fine and dandy. I looked up at the chat and all I see is what Julius wrote. You cube it. All right. All right, there you go. Sounds good to me, you guys. In the interest of time, I might just give you the answer to this one, okay? Because this one is kind of similar to the last one. So I'll give you the answer to this one, and I want you to make sure that you can do it. The answer to this one, not the solution, but the answer is 808 kilograms per meter cubed, because I want to try the last one, okay? And I'm sure that some of you have taken a look at this one already, but it's kind of a tricky one, and I don't know why I didn't give myself more space to try this one, because you need a little bit of room, but you're gonna have to bear with me, and we're gonna figure it out. It says a modern take a deep breath. Last problem in chapter 1. A modern pencil lead is actually composed primarily of graphite, which is a form or what we call an allotrope of carbon. Carbon has several forms. Carbon can be diamond, it can be graphite, it can be a nanotube, I guess. Anyhow, estimate the mass of the graphite core in a standard number 2 pencil before it's sharpened. Okay, so she gives us some good hints down here at the bottom. She says, assume that this pencil lead can be approximated as a cylinder. So do you guys remember the volume of a cylinder? Volume of a cylinder is equal to pi times the radius squared times the height, okay, if you've forgotten that. It says here, measurement of a typical unsharpened pencil gives a length of about 18 centimeters. So that would be our height, okay? That would be our height. An H by that, I guess. And what else? Subtracting the length of the eraser. Wow, we were getting picky here. It has a diameter of 2 millimeters. Okay, so I'd like to do everything in centimeters here. I just think it's going to be a lot easier if we work in centimeters. The first thing we need to do is convert the diameter into centimeters. Does anybody know how many millimeters, how many millimeters there are in a centimeter? Might be a bit of a sprain at 5:30. Yeah, thanks, Julius. There's 10, yeah. So if you take, and bear with me here, I'm going to kind of just scribble it down here, that if you have 2 millimeters, okay, and you have 10 millimeters in 1 centimeter, millimeters cancel, and you end up with 0.2 centimeters, okay? But that's the diameter, right? It even tells us right here, that is the, that's the diameter. We want the radius. So how do you get a radius? I know, you take a diameter and you divide it by 2, okay? So let's divide that by 2. Move that over here. Whoops, there we go. We're going to divide that by 2, and we end up with our radius is equal to 0.1 centimeters. So now we have the radius, and we have the height, and by golly gee, we have pi. So let's plug everything in, and I'm going to move up to the top because I'm kind of running out of space here. So we'll put the volume is equal to pi, which is 3.14, multiplied by the radius squared, which is 0.1 centimeters squared, multiplied by the height, which is 18 centimeters, okay? And when you plug all that spinach into your calculator, you get the volume is equal to 0.57 centimeters cubed, like that. All right. So there we go. Now it's telling us to estimate the mass of graphite. And you're probably like, Mr. Dion, why are you figuring out the volume? Because there's something I forgot to tell you, is that in order to solve this problem, we actually need the density of graphite. And that's left out on here. It's actually in one of the figures in the textbook. And you're like, well, I wouldn't have made that assumption. But anyhow, the density of graphite is, I have it written down here, it's 2.2 grams per centimeter cubed. And so by now, you know the formula D is equal to M over V. And so if we want to solve for mass, we can rearrange that to mass is equal to density, multiplied by the volume. So I'll switch to the green pen to solve the problem in the end, or give you the final answer, which is going to be mass is equal to the density multiplied by the volume. We have the volume, which is 0.57 centimeters cubed. We have the density, which is 2.2 grams per centimeter cubed. It's not magic. The centimeters cubed cancel out, and we end up with our final answer, which is what? 1.3 grams is what I got. 1.3 grams. Does anybody notice anything kind of funny about my answer? And I just kind of noticed this just now. Thinking out loud here. Talking to myself in my office. Anybody notice something funny about here? Okay, I'll ask you a different question then. Do I have the correct number of sig figs in my final answer? It's either a yes or a no. Yeah, Julia says no. I don't, do I? Something I didn't realize until just now, but the diameter that they gave us only had 1 sig fig. Yeah, he says it's supposed to be 1. You're absolutely right. So technically that's not the right answer, right? It should actually be 1 gram, 1 stinking gram. All right. Anyhow, the reason, and if you're like, oh, Mr. Dion, why did you go over this problem that involves cylinders and stuff? The reason why is because this was on an exam that we gave, not spring 2020, but spring 2019. Okay, I taught this class in spring 2019 at the Rampart Range campus, and we asked a question virtually identical to this on that exam. All right. There we have it. So I'm going to go back here.